introduce Ken Keller. Ken Keller arrived in Minnesota in 1964 and has been associated with the university since then, currently as Piercy Distinguished Visiting Professor. In addition to teaching chemical engineering and starting the biomedical engineering program, he had a brief stint as department head, was acting dean of the graduate school, academic vice president, and the 12th president of the university. After leaving the presidency, he was the senior vice president of the Council on Foreign Relations, and then the director of the Johns Hopkins School of Advanced International Studies in Bologna, Italy. He is a member of the National Academy of Engineering and a recipient of a Johns Hopkins Distinguished Alumnus Award. Please help me welcome Ken Keller.
Good morning to everybody. Can you hear me? Am I connected? Okay, I'm nice and loud. So we have 20 minutes or thereabouts to deal with 100 years of history. I may speak quickly. I hope what I can do is give you a sense of the progress of the connection of this department to the profession itself, to the university, and to your lives as well. And one of the places to begin is first to figure out how this works. Is to to position the remarks in the context of the University of Minnesota itself, which actually, with the territorial legislature before Minnesota became a state, they established a university. It was easier then in those days. Of course, they had no students and no buildings, so it was even easier. In 1858, then, Minnesota became a state, and they struggled to get some money and started the first classes in 1869. And the reason I put that date in is that it turned out that the first science that we had at the University of Minnesota, the first separately stated science, was chemistry. And shortly after that, we dealt with the first public pressure on where we ought to be going with the university. The School of Mines was created. It was created, it actually was established before it had any faculty members, but it stood there and it put people off for a while, as it turned out. The chemistry department was primarily a department doing service role to the rest of the university, but it then began to offer degrees, and oddly, it called the degrees chemical engineering. So the first 4 graduates of the chemistry department were called chemical engineers, although nobody knew what chemical engineering was. And then in 1902, the then head, a very distinguished chemist named George Frankfurter, wrote to the president of the university stating that we needed a chemical engineering department. And immediately afterward, 17 years later, we established the department. One of the reasons that things were so difficult is that you have to think of the context of where chemical engineering in the world was at that time. And chemical engineering, we never teach this to students, but it's a very interesting history, that it actually began with George Davis. And George Davis was an inspector of industrial machinery in England. His job was to go around and check on the safety, and he saw a lot of equipment and decided that there really was a need for a profession of people who dealt with that equipment. And so he said, let's call it chemical engineering. It was picked up, and he started lecturing in that area at the University of Manchester, quickly picked up by Norton at MIT, calling it chemical engineering. And of course it developed at MIT, not separately, but in fact there was a great division between William Walker and Arthur Noyes, which was settled in 1919, the same year that chemical engineering started here. It was settled finally that there would be a chemical engineering department centered on machinery and practicality, and Noyes left and went to Caltech. And it was after some time that they came together to realize that we needed both equipment and we needed theory and chemistry along the way. So that was the timeline of the 2 intersecting timelines, but we did begin then chemical engineering, and I think we can talk about the 100 years in 3 tranches if you want. One was what I call the 3M era. That was not the 3M you know. That was Mann, Montana, and Montilian, who were the three professors that held the fort for most of that time. In any event, it was the Doc Mann era, and it went from 1919 to 1949, in the middle of which the School of Mines and Metallurgy was established, which was an expansion from metallurgy to consider something, from mines to consider something more fundamental. So we had the beginning of that effort as well. And this whole thing was run by Doc Mann. Oh, the second era is the Amundsen Era, which we'll spend most of our time on. And the third era is what we're now spending most of our time on, which is the growth and maturation of CEMS, CEMS. I never know how we pronounce the acronym. Is there an official way of pronouncing that?
CMS.
A very practical man. That first era, the era of Doc Mann, there's Doc Mann. Doc Mann came educated at the University of Wisconsin, which is in Madison. In case any of you didn't know, I'm familiar with it. I wanted you to be aware of that. He had been well trained in Madison because he was the drum major for 7 years. And so he came here really an enthusiastic fellow, organized around a curriculum which was essentially chemistry, augmented by a course that dealt with equipment. And all the words he spoke were words about how you managed equipment. And that became really the historical basis of chemical engineering. He did that for 30 years here. And he was a very popular instructor. Not only that, but the major was very popular. And there are many people who were produced with that kind of curriculum. We were not initiators at that time. We were much more likely to be viewed as followers, as we watched what was happening in the rest of the country. And mostly it was satisfying, except in 1933, a young freshman arrived on the campus who thought it wasn't very good. He thought the idea of an applied, of dealing with machinery, of dealing with empiricism, of not understanding anything that was going on, any fundamental aspects of it, was not very satisfying. But he stuck with it. His name was Neil Amundsen. And he stuck with it as an undergraduate until he finally got his undergraduate degree, at which point he said, basta così. He didn't say that. We say that in Italy. It means that's enough of this kind of stuff. He went to work for an oil company for a couple of years and then said, it's time to go back to graduate school. He came back, he said, but I'm going to do it in mathematics because that makes some sense. And so he took his degree in mathematics and was talked into doing a mathematics course for chemical engineers, which he did very well, so much so that a group of undergraduates went to see the then head of the department, Doc Mann, to say, why don't we make this a permanent part of our curriculum? And they talked Neil into doing that. So he brought that over to chemical engineering, and he became an assistant professor of chemical engineering. He did that in 1947, I guess. In 1949, Doc Mann died tragically and suddenly, and the department was in chaos. And Neil was asked to take over as acting head of the department. He had already had some experiences in his graduate work which were beginning to give him a framework of things that he wanted to do. And he spent a year at Brown University, which at that time, and really since then, has been one of the leading centers of applied mathematics in the country. And he interacted with people of tremendous talent who dealt with each other, who talked with each other, who picked up tough problems, who loved to think about whether or not they could generalize and use mathematics in a modeling sense. And Neil was very much impressed with that and thought that's the kind of department he thought he should be managing. He then had a sabbatical which took him to Cambridge for a year, and there he encountered another group of extremely talented people who were exciting to be with all the time. He said, I know the kind of department that I want. And so he came back, and we really had the beginning of the Amundsen Era. In 1949, after a couple of failed searches, or actually he took over when Doc Mann had died as acting head, and there were a couple of failed searches which didn't produce anything. The dean said to him, Neil, it's either you or another faculty member. I have to take over his head. And Neil said, I can't stand that guy. and so I'll take over his head. Which he did. And he stayed his head and began to think about how he could build the department. And he built that department, and I've indicated this, with a hiring spree that was extraordinary, that lasted about 10 years, and developed changes which affected the profession very widely. So he had a hiring strategy that was the centerpiece of what he did. And it began with the fact that he said, you don't hire to fill a position, to fill something you've predetermined. You find the best person, and you build a proposal for that field around that person. You only hire people that are smarter than you. That takes a lot of courage. But and it actually takes a lot of ability, because he was pretty smart. And you hire first and then afterwards. It's better not to ask if you don't like the answer. It's easier to apologize than to beg. And you avoid hiring chemical engineers. So that too is very important. And this was serious with him. He says, let's hire only junior faculty who haven't been somewhere else where they learned bad habits. And that was essentially what he brought together. And so he brought together a group of people, exciting because they didn't represent chemical engineering entirely. He hired a few chemical engineers. But they came together, and then he created a cultural environment which really is the origin of what we would know today as the department. And the first was something that Dan alluded to, that is teaching as well as research. You didn't come to this department at the very, very beginning and not realize that teaching was not a very important part of it. First of all, you saw the head of the department teaching at 8 o'clock in the morning on Tuesdays and Thursdays, although in other parts of the university, heads of department are considered above that. That became something that was really followed here. He recognized that if you worked in a team teaching environment, you also had a way of taking people who were not chemical engineers to begin with and have them learn by doing, learn by teaching. And that was a very important thing. The teaching standards, there was never any doubt of the teaching standards. By the way, the idea that you did team teaching meant that you were used to having your colleagues sitting in the audience, and you came prepared. It wasn't intimidating, it was natural, and you expected that you would be prepared because you would be queried. And not only that, your colleagues in the audience could very well decide to tell you did something wrong. They could get away with it. And so that was very important. What I'd like to add to what Dan said about teaching and research that was very clear to us is that we didn't think of teaching as a service, but in fact that we thought of that as a two-way street. You actually learned by teaching. So you viewed teaching as one of the ways of improving your research, not simply that research informed your teaching. He encouraged joint research. He had seen that in all the places he'd visited, and we have one of the most collaborative departments that you can imagine. Where's Frank? Frank Bates has co-authored publications with something between 20 and 30 of his faculty colleagues over the course of time. It's a natural thing to do. He encouraged an absence of hierarchy. The day you came onto the faculty, you were equal to everybody else. That was quite clear. What mattered was your ideas. The lunch table was where we had our meetings. We still have our lunch table at the campus club. It's an expandable table. It's round, so you can fit 8 in tight packing, but you can move back a little bit and get 10 or 12. People eat in their laps at that point, but they nevertheless do that. The department was a community. It was something that went beyond a place that you worked. And you built for the future, which meant that you always focused on what you could do for the young faculty. That became a very important part of the culture. We built community by breaking disciplinary barriers and engaging people more broadly. And those of you in more recent years would be familiar with the ARIS lecture series. Every 3 or 4 years, we bring in a semester of speakers for the graduate program that have nothing to do with chemical engineering. We have a theme. We're preparing one for next fall, which is pretty close to ready, I think. And it was a very important aspect of it. ARIS, one of the ways we kept ARIS at this university was by allowing him to teach anything he wanted to teach in the university. And one of those things was paleography. So he taught Latin paleography, and he was the first and only university professor, where university meant his discipline was professor in the university. We were very much engaged as a department. Remember, what I'm talking about here is how you build community. I can remember groups of us who went down to Twin Cities Opportunities Industrialization Center and taught general education degrees to people who had to finish high school. We spent lots of time with that. We sponsored, you could read, the Firehouse Experimental Theater, which was a bizarre place, had in its acknowledgments the Department of Chemical Engineering of the University of Minnesota, because we had supported that activity. And it was a time of political activism, and the department was engaged in that. And all of that brought people together. We had a lighter side. Some of you may be familiar with the fact that one of the afternoon speakers today did an experiment in which he destroyed a swimming pool on campus and then dumped all this gunk that he'd done to increase the viscosity to find out whether swimmers could swim faster or slower in a more viscous environment. It turned out that it didn't matter, as I remember. Except to him, because he got the Ig Nobel Prize. ARIS had a very famous incident with Who's Who that we don't have time to talk about now, because Lorraine has told me that if I get too... I'm okay. Well, do that. We'll do that at cocktails later. And ARIS has written hundreds of poems for each of us, dealing with, to introduce us, to be published about us, to amuse himself and others. And it was the kind of expansion. All of these things were the informal ways in which this program became a community. And the result was this group of people. This is the 1966-67 academic year. So remember, Amundsen takes over in 1951 as the permanent head. He starts this hiring spree in about 1955. It goes on to 1965, at which point there are 14 faculty members in the department, 12 of whom he has hired. Of the group that you see here, some of us look a little younger. Of the group that you see here, 7 are not chemical engineers. They have some other background in their preparation. Of the group that you see here, 6 are members of the National Academy of Engineering today. Of the group that you see here, all of them started out, except for one, as an assistant professor. All of them stayed in the department until they retired, despite offers that come fairly regularly along the way. This was a remarkable high point in many ways. Not that we went down, we hit a mesa and we've stayed at a good place. But it was an extraordinary mark of the cohesion that he built and the excitement that he built and the environment that we had. But it also had one of the most important effects on the profession that people who write histories of the chemical engineering profession talk about. And that is an enormous paradigm shift. What chemical engineering had been under Doc Mann or under William Walker or others is centered, its thematic connection was its connection to the chemical industry. That was a very important thing, and it allowed us to do a lot of things. What happened, the dissatisfaction that Amundsen felt with being an empirical scholar of equipment was to find out what lies underneath that, what kind of analytical frameworks could be more powerful and would serve the industry, but not be limited to serving the industry. And that led to the paradigm shift in which the earlier devotion to courses that we called unit operations and heat and mass balances and lump parameter rate processes, gave way to mathematical modeling and what I call the creative leap, the birth of chemical engineering science, where we describe things as reactor analysis, transport phenomena, process control, chemical thermodynamics. And the value of that shift in paradigm was chemical engineering was now not simply going to be, it will deal with its roots in the industries that it serves, but it won't be limited to that. And that meant that we could move on to new opportunities, filling scientific gaps where basic science had moved away from continuum physics and continuum ideas into more molecular ideas. There were things left to be done, and much of the work that was being done in this department was filling scientific gaps. It allowed you to look at other systems. I myself looked at physiological systems and said, well, the issues of transport phenomena exist there. There's lots to be done there. Why shouldn't we, chemical engineers, be involved in that? The same is true of energy and the environment, the opportunities in material science. So there were a range of new areas that came about because we found that the basic identity of chemical engineering was in its analytical frameworks, not so much in what it was being applied to. And that became a very important element which allowed us to think about expanding. And it happened, it was spread across the country, including by our colleagues at the University of Wisconsin, who these two departments here in the Midwest of the United States changed the trajectory of all of chemical engineering. It's recognized widely by people along the way, and it's a very important aspect of what we were able to accomplish. So those paradigm shifts also meant that we could engage and we could pick some of these directions, and not everybody would work on everything. And it would have been possible for us to go in many directions, but what happened in 1970 was an encouraged marriage of chemical engineering and mediation. That is, get together or get out. And so we thought about that for a while, and at first negatively, but then realized that it was an opportunity. An important opportunity, and we brought in Chris McCosco, who was the first link between the two departments. But we argued that precisely because we had expanded the ideas of chemical engineering to deal with analytical frameworks, we could pick anything we wanted with respect to connections of any sort. That was the important thing we understood. And so we entered what would turn out to be the third aspect of or the third generation, the post-1970 generation, when we learned the virtue of arranged marriages. Actually, we worked a good deal. We got another building. We got a lot of positions. We did very, very well, and we brought in Chris as the first bridge, arguing that polymer processing obviously involved both ends of that spectrum. And we began a process of building and building, which didn't mean that we would ignore those other opportunities. And so if you look at the department today, its name is Chemical Engineering and Materials Science, but as Dan has suggested, it's covering many, many aspects that extend the reach of chemical engineering in many, many directions, and it's provided all sorts of ways to build on the culture we had already established of cooperative and collaborative research. So we were used to that. That was a value in the department. I'm still watching. I have 2 minutes. Okay. And we were in that period. For example, we brought chemistry back to chemical engineering. Gus Arish learned that there's something more to chemistry than A plus B goes to C plus D. As useful as that was. We had new links to condensed matter physics, obviously. We rebalanced theory and experiment. I put that in quotation marks because I'm one of those who believes that there are analytical theory and there's experimental theory. Both are theoretical approaches that we've made a distinction that I don't think is necessarily a very good one. But when we rebalanced theory and experiment, we found ourselves no longer able to deal with chalkboards and chalk. We really needed serious space. That led us to with the help of alumni, particularly George Piercy, Bob Gore, processes which built the facilities that you will see. Some of you probably haven't been back since those early days, and you ought to go through, take the tours tomorrow to see what beautiful space we have. We have gone much more in the direction of outreach. We haven't abandoned in the idea that we stay in our little cells and do mathematics. We have a Center for Interfacial Engineering, we have iPrime, we have recognized our responsibility as part of a land-grant institution, not arguing that there's an either-or proposition there either. So we're very much involved in that. So the department's much larger, and we have to have stimuli for getting people to come to faculty meetings. You may recognize a few of these people, but the department grew, and that has meant changes. It's not quite the same as it was in the heyday, but nevertheless, we have found ways of creating community, which is something we want. So this, I think, I'm almost finished now. But I did want to point out that in 100 years, there have been 1, 2, 3, 4, 5, 6. Well, I haven't included 7 department heads. Actually, 7 department heads in 95 years. Then there's this other guy. We'll see whether or not he manages to extend the years per directorship. I've tried to stop it myself, having spent only 2 years in the department head. But they have that leadership, that constancy of leadership is a reflection not only of the quality of the people who did the leading, but the confidence and sense of purpose that the whole department has had in supporting people and being willing to work with them and willing to delegate authority to them, to be convinced by them, to work around the luncheon table at the campus club with them. So I won't leave with, if you go in the main office, you'll see these 4 gentlemen honored. I think it's a very important point to recognize. Not that they were the only people, but they were so symbolic of the department. We have 2 mathematicians, a chemist, and a chemical engineer. That these were people who have established, many of you worked with one or more of them. And they were an extraordinary part of the department, as well as personal friends to me, to Chris, to Ed Cussler, to people who knew them very, very well. And it would be wrong to end the story of history without not calling attention to these 4 who meant so much to us. But the legacy and what we will think about for the rest of the day today, the opportunities, are something else that has been transmitted through the values in the department. And what we give to the future is the building blocks of an innovative culture. You need the right people, and you have to spend a lot of attention bringing in the right people. And when you bring them in, doing everything you can to support them. Learning to communicate across disciplinary boundaries, avoid hierarchies, seek generalization. And I refer to an Arthur Koestler insight. Arthur Koestler argued that creativity was not so much discovering new things as discovering connections between things you already knew. And that is called bisociation. And that's much of what we are involved in here, as we find new collaborations, new ways of joining one to the other. It's been an extremely proud history, and I sometimes use the term saying we managed to live with Camelot for those years. I think that the department is well positioned to continue that for the next 100 years. Basta.